I'm Zoltan. I'm a faculty at UT Austin. I'm welcoming you to this workshop at NeurIPS on the CityLearn Challenge 2022. We'll have a great program, so sit back and relax. Let me share quickly my screen so to show you what we have planned for today. There we go. So, here we go. So we're here to talk about the challenge that we have organized over the past 4 or 5 months throughout the summer. With me today here is Kingsley, who helped run behind the scene things, as well as Siva, who you'll hear from pretty soon. The program for today, what you probably have seen, I have a few slides just to kick us off, and then I'll hand it over to Siva from EPRI, the Electric Power Research Institute, who are one of our sponsors and also data donators for this challenge. And they'll put the challenge in a bit of a bigger context. And then after that, we'll show you, for those of you who haven't participated in the challenge or here for interest, I have like a 6-7 minute video that summarizes everything. And then this will be followed by presentations of the top five teams of the challenge. The order is alphabetic, so don't interpret anything. After we've done with presentations, at the end, we'll announce the top 3 winners of this challenge. And then at the end, at the very end, we have some time to meet in breakout rooms if you wanted to have a chat with the teams individually, and then we'll be good. So it's about a 2.5-hour program. 2 to 2.5 hours. We should have time for questions. Feel free to ask as we go. There is some buffers built in if there's anything unclear. But other than that, please enjoy. This is a celebration also of the hard work that y'all have been put into it. So hopefully, we enjoy and we see what came out of it, and then we move this field forward. Okay, so a few things I wanted to give before I hand it over to Siva. First of all, a lot of people behind the scenes. I mentioned Kingsley. Him and Deepam from AI Crowd really did the technical part, setting everything up, dealing with bugs and making sure that the software is running as it should be. Big thanks, of course, EPRI, like I mentioned, our sponsors, providing especially the data, which is hard to get by, as most of you know, these days. So that's big things. And then a lot of external advisors from national labs, PNNL, Berkeley, as well as CU Boulder, to help us shape this into what it has become. And then, of course, thanks to AI Crowd to executing the challenge in a professional way and then gathering attention. We had a lot of submissions. Another sponsor besides EPRI, who sponsored the main prizes, SIG Energy, with the special interest for energy informatics, that is organizing the BuildSys and the e-energy conferences, also decided to sponsor us with travel grants for community prizes. So we'll have 3 of those also at the very end that we will be giving out. And then lastly, Amazon provided compute credits to run all the computations on servers so that we can run the challenge. Voila. So with that, and already way ahead of time, I will hand it over to Siva, who will introduce us the bigger picture from EPRI. Siva?
Great. Thank you, Zoltan. This was excellent introduction. Thank you for that intro. Are you able to hear me okay?
Yes.
Great. All right. So let me see if I can share my screen here. Yep. Okay. Let's see. Yeah. Are you able to see my screen?
Yes.
Yeah.
Great. Okay. So yeah, welcome everybody. This is as Zoltan mentioned, this is a celebration, and we are very excited to have you all here. And I've been sitting pins and needles, like many of us who've been involved in this, to see what came out of this and who the winners are and so on. But before that, I wanted to kind of set a little bit of context to the overall to the competition, why EPRI was involved in it, and how we came about doing this. So it's sort of taking a step back and taking a look at the big picture. EPRI over the last several years has been sponsoring a concerted effort on bringing together energy management, energy professionals, professionals in the electricity and energy space, power engineering space, alongside of AI practitioners, both in industry as well as in academia. And we have identified a set of 5 what we call grand challenges. One of the grand challenges is this notion of grid interactive and smart communities. This is the idea of making our communities integrated better into the electric grid, so as to be able to be responsive to the grid conditions, and also to serve and also for the grid to kind of help the individual customers have better service. So the sort of the idea here is to create this this collaborative environment. And so that's the basis for some of the work that we have done here. So just to give you a little bit of context for those who don't know what EPRI is about. So EPRI has been in operation for about 50 years now. We are a not-for-profit the research and thought leadership organization. We conduct scientific research related to electricity end-to-end, all the way from generation to use. And the members of EPRI are typically the utilities, and also we have we do a lot of work with governments through government grant writing and grant funding. Our work typically focuses in on all the way from emerging technologies in this space to understanding the customer behaviors to the idea of rate setting and so on and so forth. And we bring in a lot of collaborative value in this process of being able to bring different stakeholders in the energy ecosystem together. So in a nutshell, we started in 1972. Some of our major milestones along the way, in the year 2000, we started a concerted effort on electric vehicles. And EPRI was probably involved in almost every single US electric vehicle viability R&D study. Then about 2008, we started looking at the idea of residential and commercial applications for energy efficiency. And then in 2015, we were one of the very first organizations to co-develop alongside a major home developer, the concept of zero net energy grid interactive communities. And we've been doing this sort of work since then. So we've had a long and enduring legacy as far as collaborative research is concerned. And what we're trying to do now is to accelerate the transformation of the energy ecosystem towards a more decarbonized system. So when it comes to decarbonization, EPRI works in several areas, all the way from some of the policy, market, technology drivers, and a specific set of strategies and utility actions that can all support the concept of community or energy or economy-wide decarbonization. But what we are specifically focused on, as far as this topic or the topic of today's discussion is concerned, is in the notion of demand-side flexibility, which we largely work on flexible loads. These are loads on the behind the meter that can be flexed in response to certain grid conditions or in response to certain economic conditions. There is the notion of distributed energy resources, be it rooftop solar, battery storage, thermal storage, et cetera. And then to the larger notion of connected communities, EPRI is leading a connected communities project sponsored by the Department of Energy alongside 9 other projects in this space. So all of this work is, the upshot of all of this work is that we have generated a lot of data from the field demonstrations that we have conducted since 2015 in the process. So that's the genesis of the data that we have. But again, the grand challenge itself, what is it? So the idea is that we are seeing all these trends out there, be it the proliferation of Internet of Technology devices, the adoption of electrified end uses in the form of heat pumps and heat pump water heaters, induction cooktops. There is an upswing in the market adoption of these technologies. While these technologies are largely meant as a way to help customers feel more comfortable, do their work better, be more safe, et cetera, they are all sort of electricity and energy impacting. And so in that sense, they also play a role in being able to provide the flexibility that is needed if should a grid condition arise where they have to be able to provide that sort of service. So we take advantage of that through this notion of grid interactive and efficient buildings and to the concept of local energy communities. But through the grand challenge, what we're trying to do is to establish a forum where we bring in different stakeholders, research folks from the power sector, as well as AI practitioners, to help and demystify how AI is applied in building applications. The utilities are still sort of trying to figure out if this AI thing is for real. And what we are trying to do is to effectively try to identify the cases where AI ML can definitely help produce a proper business case for them so that they can make the right sort of investments in those technologies for data collection, as well as training those AI algorithms and also making sure that these can work in concert with the customer and their expectations. So the idea is to connect the dots and show how AI can help in this space. We've done several activities over the year. We've curated some high quality research in this space. We do quarterly webinars. We have organized an AI and electric power summit this October in Rome with international participation. And we have also gone about looking at funding opportunities to help further this work in collaboration with several of our members and several of our collaborators here. We have continued to highlight the current successes to our utility members in this space and the emerging trends. The big acknowledgement is that we are facing a big problem. It's a big problem, as in a capital B, as far as decarbonizing communities are concerned. And there is no real silver bullet here. There's no one single technology that's going to make it all happen. We have to take an all hands on deck sort of approach to this. What we need to do is to work smarter, but also harder, unfortunately, because there are chasms to cross. But we do identify where we are successful. We celebrate those successes. Where we are finding challenges, we address them head on. So that's sort of the approach that we have been taking. And this has resulted in a lot of good activities. This is just a smattering of some of the ongoing current activities. It doesn't mean that these are the only things that are happening in this space. There are several utilities that are participating in applications, have instituted applications for advanced controls. And we have the big challenge that keeps popping up for us is the idea of making any sort of control solutions, whether it's learning-based control or non-learning-based control, to make it to make the implementations easy and explainable, which is a big and important issue, because without explainability, there is a disconnect between what customers can perceive, what the grid operators can perceive, and what is really being done through control actions. And there are several emerging questions that are sort of popping up for quarter 2022. for example, is one of the policy drivers that has brought in these sort of questions. The idea of being able to use a combination of distributed energy resources, heterogeneous combination in the form of solar, storage, battery, on-site wind, et cetera, in addition to loads, and looking at it in a more orchestrated control fashion. So these sorts of questions are emerging, and I think AI is absolutely the right sort of tool to be able to help handle some of these questions. As far as our projects are concerned in the space of grid interactive and efficient buildings, we do a variety of activities all the way from technology scouting and assessment through our technology innovations program and all the way to demonstration and deployment. And along the way, we have developed value frameworks. For example, we have developed a value framework that can help identify when demand flexibility is suitable, the conditions under which the rates and decarbonization of the grid support some of these activities as far as controls are concerned, so as to be able to provide a win-win solution for the customer and for the grid. We have looked at functional requirements for standardizing activities. We convene several webcasts and stakeholder discussions. And of course, we do demonstrations and collect a ton of data in the process. One of the areas that we've been recently focused in on is the concept of multifamily housing demonstrations. So although the challenge today is based on data from several zero net energy single family homes that we had conducted a while ago, our more recent research is focused in on multifamily demonstrations. We've been looking at multifamily, but also specifically affordable housing in multifamily, because the concept of equitable decarbonization is something that is true to our heart. Our research work is largely oriented towards societal benefit. So we are looking at equitable decarbonization as an important and milestone in being able to achieve that societal benefit. We do several demonstrations in this space, all the way from, again, use of cutting edge technologies to connected communities, to looking at all electric communities and so on. The upshot, of course, of all of that is that we have a lot of data in this space. We've been specifically looking at several technologies that are what are called retrofit ready. Again, within the multifamily space, the harder problem to tackle is one where you are going in and retrofitting these buildings to make them more energy efficient or bring them up to code. And this is a challenge because many of these multifamily communities are extremely capital sensitive. These projects are capital sensitive. So requiring a combination of appropriate business models alongside the technology choices is of importance here. Requirements range all the way from not, many of these buildings being sort of historical and so on, not requiring major changes to the facade, to something like making sure that you're working on a shoestring budget, right? And to make sure that the operating cost of all of these technologies does not accidentally cause an increase in the energy burden for several of these communities that are already kind of affordable housing, and so they are low-income customers. So overall, there's layers of challenge that we have been trying to focus on, but we've been tackling these problems head-on. And again, we've through the process of demonstration, we have acquired a lot of qualitative insights, but are also collecting a lot of data and are able to kind of characterize the performance of some of these in a more meaningful way. Our main takeaways, of course, from doing all of this, which is where I think we are with respect to the challenge today, is that demand flexibility or demand side flexibility, grid interactivity, et cetera, they are a very important tool in the arsenal as far as decarbonization is concerned. However, they're not the only ones. As practitioners in this space, sometimes we feel like, oh, everything has to be, all roads should lead to demand flexibility. And the reality is that it's not the case. Sometimes demand flexibility is the right answer. Sometimes it's plain old energy efficiency that's the right answer. And other times it may not even be electrification, right? It could be the use of low carbon fuels. So a decarbonization can happen along multiple pathways. The industry players, especially the utilities here, are sort of still unboxing this notion of demand flexibility. They are familiar, they are very used to the idea of doing demand response, being able to flex the grid, or to send out emergency flex messages in the state of California to reduce your energy use during critical times of the year. But that happens 1 or 2 times a year. And of course, as extreme weather events continue, that happens a little bit more often. But nonetheless, it's not something that is bread and butter yet for the utilities. So that's one of the areas where we are helping them. They're sort of unboxing this notion of demand flexibility and grid interactivity. It's still nascent. When we talk about building technologies, we understand the trends here, the trends of rapid technology change. The use of IoT, for example, is definitely transforming the space from one where there is significant level of flexibility or connectivity that is available, and with these being energy impacting decisions, even though every time you change your thermostat, the driver for the change is improved comfort, the need for comfort. However, it is an energy impacting decision. There's a secondary impact, a derivative impact of that decision, which goes to impacting your energy use. And the idea is to make sure that these technologies and the customers are aware of that. And then, of course, understanding that the primary role is not energy management. This is sort of the sobering notion, because does the customer really care, right? So that question comes up a lot. And in many cases, one could argue that they shouldn't, because they should be caring about their comfort. And it's up to the technology to make sure that the technology works in a way that is energy efficient. And the answer is yes, that is indeed the case. And but the customer has a role to play because after all, it is an energy impacting decision. So if you kind of take this broad brush approach, we find that go and electrify everything, or make everything energy efficient, etc. So that sort of broad pictures emerge. However, the devil is always in the detail, right? So we need to be more nuanced about understanding the conditions under which several of these strategies can actually help. But the good news for us is that while the devil's in the detail are in the data. So needing to collect more data and to have this data more available to the larger sort of community is of primary importance to EPRI. And then of course, we are, collaboration is something that is it's integral to our DNA. The answer to several of these questions that we have asked in the past, there's this one incontrovertible answer that keeps coming up, which is that we need more collaboration. And it's in that interest of the collaboration that we have sponsored this, this event. We have provided the data, and we are simply overwhelmed by the response that we have gotten for this. I have the sort of this great honor of talking at the AI and EPRI's Power Summit, AI and Power Summit that happened in Rome. I was in a session where we were talking about data science challenges, and there were a couple of other presenters who presented their data science challenge. And when I presented mine, I saw that there was an order of magnitude higher participation that has happened for this CityLearn challenge relative to some of the other challenges out there. So I'm really overwhelmed. I'm this could not have happened had it not been for your interest as an audience, but also thanks to the efforts of Professor Zoltan Nagy, Kingsley, and several others who have contributed to this. So yeah, looking forward to what's next. Looking forward to the presentation by our top 5 teams, and looking forward to hearing who the winners are. So let me pause and see if you have any questions, and I'll transition it over to Zoltan.
Wonderful, thank you, Siva. Any questions or comments for Siva? Okay, good. Well, thank you, Siva.
Of course.
And if questions come up along the way, you want to chat with Siva, feel free to reach out to him, yes, or through me, or flag him down. He's California, so thanks for waking up early again worries, for us.
Of course.
Wonderful. Okay, so the next item on our agenda is the competition video that I will show, and that's like a 7-minute video with just music in the background, so you can enjoy it as you wake up or as you are hanging in there while it's late. The first 3.5 or so minutes is the general background on grid interactive buildings and energy in buildings, and then the second part is more specific about the challenge, the data set, how it was set up, how it was organized. There's no speaking, it's only a little bit of a music in the background, so enjoy it. Kingsley, I will run it. I'm not sure if the music will be heard, so you will ping me if somehow the music is not running in the background. So that's all. 1 second.
Okay.
All right, I'm sharing it right now. 1 second.
Hey Zoltan, do you want to try hitting the play button?
Say that again, Kingsley, sorry.
The play button. I think you might need to hit the play button because it's still loading.
Yeah, 1 second.
Okay.
All right, welcome back. And so with that, I hope we're all ready for the presentation. So let me just quickly show you where we are with that. 1 second. I will show the program one more time. We're right here. Oh, sorry. Before we do that, let's all turn on the screens and get a screenshot of our faces so we have something to remember. And then we do the presentation. So let me stop here. And then afterwards, we'll start with the Team Ambitious Engineers and Team CUFE afterwards. So first, picture time. Okay, here we go. Right. 1 second. Oh, thank you, everyone.
All right, I'll take it in 5. Oh, actually, I'll put 10.
Give it a minute. Videos are coming on. Hold on. It's good to see your faces. Thank you, everyone.
Okay, in 5.
Yeah, go ahead.
4, 3, 2, 1. I'll take one more. All right, all good. Thanks, everyone.
Wonderful. Thank you, Kingsley. All right, and with that, I'll hand it over to Team Ambitious Engineers. Matthew, right. So just so everyone on the same page, we have the presentations are about 10 minutes. We do have time for questions. So feel free to ask, and then, we continue. All right, Matthew, your floor is yours.
Okay, thanks. Let me share my screen. And can you hear me? All right.
We can hear you.
All right, thanks. So I'm presenting on behalf of Team Ambitious Engineers. And so some background about us. I'm a PhD student at the University of Washington, and I have prior industry experience as a data scientist, in particular at a startup called Shifted Energy, where I've done a lot of energy forecasting. My teammate Sorpong is a master's student at the University of Hawaii, and he has prior industry experience as a software engineer. A bit more relevant background about us as a team. He and I met while doing a water heater optimization project at the University of Hawaii. And I went on to do my master's thesis on water heater optimization. And I think this is relevant because it's possible to view a water heater as a type of battery. And water heaters by design store energy, and we can charge them on demand. The only problem is that water heaters, they sort of discharge randomly because we need to wait for someone to use water first. And they're sort of leaky in the sense that they lose some of their energy to the environment. So they're not the best battery, but we found that a lot of the techniques that you can apply to water heaters, you can also apply to batteries. And so I think that experience helped us a lot in this competition. So this is a high-level overview of what I'll talk about. So first, in phase 1, we broke our approach up into single-agent optimization, followed by multi-agent corrections. So for the single-agent optimization, we optimized the agents with dynamic programming. The main challenge was handling the grid costs, because the grid costs at the current stage depends not only on your current action, but possibly on future actions. So instead of optimizing with respect to the competition's cost, we optimized with respect to this proxy cost. And the idea here is to penalize actions that lead to large energy consumption. So yeah, the proxy cost here starts off like the normal average costs, but then we add these penalty terms. So you penalize in particular an agent's net energy, the absolute value of that, the net energy squared, and the net energy cubed. This proxy weight, they were just hyperparameters that we tuned. So once we had the single agent actions, we tried to improve them with a multi-agent model. And in particular, we used a multi-layer perceptron and trained it with CMAES, which stands for Covariance Matrix Adaptation Evolutionary Strategies. Mainly, we use that as a black box because it was easy to use, worked basically off the shelf. There's only one hyperparameter to tune, and it was fast because it was parallelized. So the input to this model, we took in the current observation, we took in the single agent actions and converted those to energy usage. And then we calculated some features for the group, like the total energy consumption and the total energy consumption of the previous period. We also fed in future values of solar generation and the emission costs and price for power. Our approach for phase 2 and 3 was very similar to phase 1. The main difference here is that we replaced future values with forecasts. And instead of deep dynamic programming, we used, again, another multi-layer perceptron. So for forecasting, we kept things pretty simple. Solar generation, we used a multi-layer perceptron trained with SGD. The inputs to the model were lags of each building's solar generation. And we also found it helpful to use leads or feature values of the average phase 1 solar generation. And the reason why we think this works is because, like, as we saw in the video earlier, the buildings came from basically the same location. And so all the solar profiles were highly correlated with each other. So in this case, it helped to use sort of this phase 1 feature information. For non-shiftable load, it was very similar. In this case, the leads didn't help, but we did find that seasonal exponential smoothing features helped. Now that is exponentially weighted moving average, and the seasonal part just means we looked at different groupings. For example, we calculated the non-shiftable load on Mondays at 10 a.m. So on the modeling side of things, in red shows sort of the difference from phase 1, but overall it's very similar. Instead of using dynamic programming, we optimized the single agents with the MLP. Again, we had a multi-agent model that learns to correct single agent actions, and everything was trained end-to-end with CMAES. Yeah, we also replaced future values with forecasts. So this is sort of a high-level overview of our approach. It's not meant to be super detailed, mainly meant to show the similarities between the two phases. So again, in phase 1, we had a single agent model, which we optimized with dynamic programming. We fed those single agent actions into a multi-agent model, which learned to correct or improve the single agent actions. In phase 2 and 3, it's basically the same, except we replaced DP with an MLP and future values with forecasts. And this dotted line just shows that everything here was trained end to end. And so what we didn't do was train the single agent MLP and then feed the input into the multi-agent and train that separately. Everything here was trained all at once. Some additional ideas that we thought of but didn't have time for. Well, I didn't go too much into our future engineering But one low-hanging fruit that we thought of after the competition was to calculate like the group's monthly max, like a run-in monthly max. That probably would have helped to optimize the grid cost. On the forecasting side of things, you might have wondered why we used an MLP, not something fancier like an RNN or a CNN. And it's mainly because it was fast, and we tried an RNN, got similar results to an MLP. It's just the RNN was like 10 times slower. But you could probably get better results with the better architecture here. On the modeling side of things, we wanted to try and model predictive control. We had all the ingredients for it, just not the time. And for optimization, RL seems like the natural method to use here, but we kept things simple and used a black box optimizer. But it seems likely that RL can do better. So that's all I have. We'd like to thank the organizers of the competition, and in particular the CityLearn and AI crowd teams. I think this type of framework it's very important for these types of optimization problems, and I think a competition it's a great way to benchmark techniques and promote ideas. So thanks again to all the organizers, and thank you for listening to our team's presentation.
Thank you, Matthew. Very nice talk. Any questions or comments for Matthew?
Yes, I have a question.
Go ahead.
Thank you for the presentation. I was wondering, how do you guys use the predictions of non-shiftable load and solar generation?
So the model itself is just like an MLP, and so those are just inputs, more features that you put into the MLP.
Oh, so they go as inputs to MLP of the reinforcement learning algorithm?
Yeah, I mean, we didn't use RL, but yeah. Yeah, it's just
okay, got it.
to the model, right?
Okay, got it. Thank you.
Okay, thank you. I will say it's interesting you mentioned thermal storage in the beginning, because when we started CityLearn in 2017-18, the first version actually used thermal storage, and only this year we transitioned into electric storage. In the system you can do both, but for this challenge we actually we clipped for electrical. So that's interesting. Another interesting parallel is the original creator of CityLearn, Jose, moved to Hawaii after he finished his PhD, and he wanted to join today, but he said it's too early after all, so he couldn't make it. But so it's quite interesting to see these parallels. Cool. Thank you, Matthew.
We have one question from Julian.
Oh, go ahead.
Yes. Hi. Very interesting. I didn't really understand the single agent and the multi-agent, what each of them were doing exactly. What's kind of the output of each of these two models?
Yeah. Right. So the single agent model just outputs an agent, an action for each agent. And then the multi-agent model, you can think of it as like we added corrections to the single agent actions so that it was the collective actions of all the buildings were good for the group.
Yeah, okay. Yeah, makes sense.
And then there's, oh, sorry, go ahead.
Sorry, I also have a question.
Go to.
All right, thanks for the presentation. I have two questions actually. The first one is you mentioned using 10 future values of solar generation. Could you elaborate on how that helped?
Yeah, so if you want to know what the best action to do now is, you might want to, I mean, you do want to look at the future if you have it, like solar generation, just like you would want to look at the future price for power. And so those are like relevant features that you would want to input into the model. we only used it for phase 1 because, well, we don't have access to future values in the other phases. So in the other phases, we had to forecast the solar generation.
Okay, thank you. And then the second question is about your evolutionary strategy you used. Did you use it to the CMA-ES, right? You said you used it to train your MLP, correct? So did you use it to search for the MLP architecture or for just optimize some parameters?
Yeah, just optimize the parameters. Instead of like gradient descent, we used CMA-ES.
Okay. All right, thank you.
Okay, wonderful. Any other questions? Good. And if other questions come up in mind, that, like I said, there is some time at the end where you can also meet individually. So not a problem if you forgot. All right, next speaker up is Team CUFE, although I think it's a single person team. Michael Ibrahim, is that you?
Hello.
Floor is yours.
Okay, thank you. Let me play a video that I have prepared.
Yeah, Ibrahim, there is no sound, or not really well.
There is no sound?
We can't really hear anything. We can hear you when you speak, but I can't hear the video.
Okay. Okay, can you hear it now?
No, it's very faint in the background, so I'm not sure. I think it's coupling through your own speakers and microphones, which will not work probably.
When you share the video, you need to hit, I think it's share sound, and also optimize for video quality.
Can I find the share sound? Share sound. And generations and the predictor for carbon emission. Finally, I'm going to describe the model predictive control system used. The developed system works as follows. The MPC uses the design parameters 24 steps ahead predictions of the produced and consumed energy and carbon intensity. Also, it uses the current battery storage and the produced and consumed energy at the current step by the building, and the MPC produces a charge or discharge decision for the building. Also, in this system, the produced and consumed energy predictors are time variant. So they use the current observation of the produced and consumed energy to update their parameters. For the energy generation prediction, first I trained a linear regression model to estimate the generated energy at building J based on the observations of the generated energy for the given 5 buildings. The parameters alpha 1 to alpha 5 are updated every 168 steps of the simulation based on the actual generated energy at building J. This kind of model is motivated by the high correlation between the generated energy of the buildings. As you can see, the correlation between building 1 and building 5 is 0.98, and the correlation between the generated energy in buildings 2, 3, and 4 is almost 1. Then I trained a second linear regression model to estimate the generated energy at building J based on its historical observation, where the matrix sigma is calculated offline based on the historical generated energy for the given 5 buildings. Then, during the simulation, the generated energy at building J is estimated based on a linear regression meta-learner. The parameters of the meta-learners, beta 1 and beta 2, are updated every 168 steps of the simulation based on the actual generated power at building J. Finally, I train my forecast based on a minimum and a maximum estimate calculated at each step based on the generated energy of the given 5 buildings. As a final note about this estimator, numerical experiment shows that this estimator is very accurate. For the energy consumption, first I trained a linear regression model to estimate the consumed energy at building J based on the observation of the consumed energy for the given 5 buildings. The parameters alpha 1 to alpha 5 are updated every 168 steps of the simulation based on the actual consumed energy at building J. Then, I trained a linear regression model to estimate the consumed energy at building J based on its historical observations, where the matrix sigma is calculated offline based on the historical consumed energy of the given 5 buildings. Finally, during the simulation, the consumed energy at building J is estimated based on a linear regression meta-learner. The meta-learner parameters, beta 1 and beta 2, are updated every 168 steps of the simulation based on the actual consumed power at building J. Numerical experiments show that the root mean square error of the estimated consumed energy after 24 steps is almost the double of the root mean square error of the estimated consumed energy after a single step. For the carbon emission predictions, I have trained a nearest neighbor regression model based on the carbon emission file given in phase 1 of the competition. This model produces perfect predictions since the file used in the training of the model was used during the final simulation. Now, let's introduce the model predictive control parameters. C hat I, the difference between the estimated produced and generated electricity. Pi, the price of the electricity at step I. II, the carbon intensity at step I. P hat no, the total price of the electricity for the next 24 steps if there is no battery, and it's calculated using C hat I and Pi. I hat no, the total carbon intensity for the next 24 steps if there is no battery, and it's calculated using C hat I and II. R hat no, the total RAM for the next 24 steps if there is no battery, and it is calculated using C hat I. M hat the maximum net electricity consumption during the previous 730 steps. L hat the load change weight, and it is equal 1 over M hat multiplied by 1 minus the load factor if there is no battery, and it is calculated using the observation from the previous 730 steps. In the beginning of the simulation, M hat and L hat were initialized using the average of the historical values of the net consumption of the given 5 buildings. The model predictive control uses the following variables: Xi, the decision at step I, Si, the battery storage at step I, N plus I and N minus I, which are the positive and negative parts of the net energy consumption at step I, Ri, the RAM variable at step I, L, the slack between the maximum net consumption, M hat, and the current positive part of the net consumption, N plus I. The model predictive control can be described by the following objective and constraints, and after solving this linear program, the decision x0 was used as an action for the building. The first part of the objective is the total price of the purchased electricity normalized by the total price of the electricity when there is no battery. The second part of the objective is the total carbon emission normalized by the total carbon emission when there is no battery. The third part of the objective is the total ramp normalized by the total ramp when there is no battery. The fourth part of the objective is maximizing the load factor, and this can be achieved by maximizing the average net electricity consumption, or in other terms, minimizing the negative part of the net consumption, and by minimizing the maximum net consumption, or in other terms, minimizing the slack L between the maximum net consumption M hat and the positive part of the net consumption N plus I. Finally, I noticed that the error in C hat I after 24 steps is almost the double of the error in C hat I after a single step. So I use this factor in the objective to reduce the effect of the error in the late estimates. The first set of constraints are the electricity conservation constraints. The first constraint means that the net electricity equals the storage decision at the previous step plus the consumed energy minus the produced energy. The second constraint means that the battery at step I plus 1 equals the battery at step I plus the storage decision at step I. We can note that S0 is the current battery storage of the building. The second set of constraints are the ramp constraints, and they mean that the ramp at step I equals the absolute value of the difference of the net electricity consumption at step I and the net electricity consumption at step I minus 1. Also, we can note that N plus 0 and N minus 0 are the current positive and negative net consumption parts of the building. The third set of constraints are the slack constraints. The final set of constraints are the bound constraints. We can see that the decision variable x of I is between -1 and 1, and the battery storage Si is between 0 and 1, and the remaining variables are non-negative. Thank you.
Thank you, Michael. Nice presentation, man. Any questions or comments for Michael?
I have a short question. It was hard to comprehend fully what the general idea for the forecasting model of it is. Do I get correctly that it's a linear regression model and it's built on some sort of a moving window of 168 steps? Can you please elaborate on the forecasting setup?
For the forecasting decision, I used two initial forecasting. The first one uses a blending or an average of the given buildings, and the other one uses the historical observation of the building. Then I take some kind of average or between these two linear regression models using another linear regression. And the weights that I'm using for forecasting, alpha here and beta here, are recalculated every week in the simulation, 168 steps. That I have done for the energy generation and also for the energy consumption.
Okay, so do I get correctly that you make the assumption that the buildings of the unseen data are similar to the 5 training buildings, and then you take a weight of the future value of the buildings that we know?
Yes, here the assumption is that we can observe that there is high correlation in the energy generation. And also you can expect the human behavior to be similar if you have a long history. So what we are doing now at 4 p.m. is what you have done yesterday at 4 p.m. or last week at the same time. So it's more like adding some seasonality and taking that into account. So instead of generating instead of training an AR model at round time, I calculated the variable offline and just used it.
Thank you. Very interesting.
Thank you.
Okay, any other questions for Michael? Good. Okay, thank you again, Michael. We'll move to the next part is a short break. So we had a good start, good first presentations. We'll take a quick break and we'll begin 20 minutes past the hour, wherever you are. So it's 8:20 local time, but wherever you are, 7 minutes from now. See you then. And then the next presenter is Div Model, Team Div Model. Okay, I hope you had a good quick break. Welcome back to the second part of the show. And we will continue with Mansoor from Team Div Model. Mansoor, the floor is yours.
Hi, everyone. Can you guys hear me?
We can hear you.
Great. So we are Team Div Model. My name is Mansoor. I'm a master's student at the University of Alberta. And I had a great pleasure of working with Jihu Yang, a research engineer at Zoya Bank Education Technology Company, and Daniel May, PhD student at the University of Alberta. So this is a brief overview of our overall method. We first look at the observation from the environment and compare it with training data set. If they match exactly, we just use our deep model agent that was overfitted to training data. Otherwise, if they don't match, it means that we can confidently say that it's an unseen building, which means building is from validation of test. So we use two models to generate actions. One is our rule-based controller, and another is our deep model agent, which was not overfitted. And as a final output for unseen buildings, we use the average of the two actions. In this presentation, I will explain both the rule-based controller and deep model agent. So RBC is a decision tree with two levels. So it needs to make two decisions. And it relies on predictions of fixed load and solar generation for one upcoming hour. So load and solar are predicted, and delta is equal to their difference. If delta is positive, meaning load exceeds solar, we want to discharge. And we try to discharge by the amount delta, but we also put a cap on the maximum discharge rate, and it is based on the hour of the day. If hour of the day is from 16 to 20, then we know that prices are higher than usual, so we call it a crucial hour. So if next hour is crucial, we allow discharging by up to 40% of the battery capacity per hour. And if next hour is a normal hour, we only allow discharging by 10% of the battery capacity. And for charging, if next hour is crucial, we actually prohibit charging it completely. So there are some, we found it to be good decision empirically, but some explanation might be from training data, it seems that solar is rarely exceeding the load during crucial hours. And most likely if delta is predicted to be negative, it's a wrong prediction and mistake costs a lot, so we don't charge. But if next hour is a normal hour, then we charge by the full amount of the magnitude of delta. And all these hyperparameters, all these parameters were selected after some trials and errors on training data set and after submitting to the competition and getting results on validation sets. So we were able to utilize only predictions for the next hour. And for predicting fixed load, we used XGBoost regressor because it's really fast and generalizes quite well. Features we used were synchronous transform month, hour of the day, and one hot transform day of week. Fixed load for the past 24 hours of a building. So this is a prediction for a single building only, by the way. And similar to other teams, we kept a history of fixed load for each hour of the day. So there were 24 separate histories. And as a feature, we included past 16 days average of the next hour, for the next hour. To arrive at this model and features, we made lots of trials using cross-validation. And here are 5 cross-validation prediction accuracies. And our score we achieved was 54%, which is quite decent. Predicting solar was much easier, just linear regression, and features solar generation for past 2 hours, and average solar generation across train buildings for the past 2 hours and for the next hour. And our score, like in other teams, was very high. Now I'll go over Deep RL agent. So again, half of the action comes from Deep RL agent, so it's quite important. It is single decentralized soft actor critic, and there's one soft actor critic per building, but all buildings share the same soft actor critic, so it's just one agent. So I will list some important features that we added. For individual features, we included building ID, which was 1 hot encoded, and IDs run from 1 to 5. From the previous time step, we included carbon intensity, fixed load, solar generation, and electricity prices. Also, we included past 16 days averages for fixed load and solar generation for 4 future hours. First next hour, second next hour, 6th next hour, and 12th next hour. And to do well on cooperative objectives, we included district features, which are averages for some features taken across buildings. These are features like fixed load and solar generation, and same past 16 days averages as in individual features case, but averaged across buildings. Okay, some tricks. During training, we did normalization of observations and rewards. So we first ran 5 simulated years with random action sampling and collected means and standard deviations of observations and rewards, and it helped a lot. And episode length was 1 week. And this is from the point of view of the agent, our agent. And during evaluation testing, if you remember, I mentioned we included building ID into observation, but those building IDs corresponded to training buildings. So for unseen buildings, we chose to do this procedure. So for any given unseen building, agent computes an action 5 times with different building IDs going from 1 to 5. And for each ID, it outputs an action and the standard deviation of the policy, which measures the confidence in that action. We assigned a weight equal to 1 over standard deviation to each action. So the more confidence in the action, the more weight we give to it. And the final action of the Deep RL agent is 1 over STD weighted average of the 5 actions. We found it to significantly outperform the simple averaging case. Model we used was quite simple. It's a standard soft actor critic, but with auto-encoder in top. So encoder produces efficient latent representations, which are passed to separate critic and policy networks. And the decoder is trained to reconstruct this latent representation. So we found that this autoencoder architecture significantly improves the speed of learning, but we are not sure if it is good for generalization. And the last important piece in our work was the reward function. We made a custom reward function. So we first computed costs, individual building costs. For the price, it's positive net load multiplied by electricity price, and for carbon, it's the same but multiplied by carbon intensity. And ramping is absolute value of the difference between district net load at this time step minus previous time step. And for load factor, we're looking at a rolling window of size 730, which corresponds to 1 month. And we took 1 minus average to peak ratio over that window. To compute the reward, for example, for price, we computed price cost for no battery agent minus price cost for our agent. And we divided it by the price cost of a no battery agent over a whole year for all buildings. Numerator gives the relative cost savings, and denominator ensures that different rewards have the same scale. And very similar formula is applied to all the other components. And final reward is a weighted sum. Okay, and to sum up, we showed our method, which uses role-based controller and deep parallel agent. And each method's weight in the action taking is 50%. And these are our results. We were able to achieve 30% reduction in overall costs on training buildings and almost 20% of cost reduction on validation buildings. So that's everything for our team. If you have any questions, please feel free to ask today or send email to any of these addresses. Thanks a lot for your attention.
Wonderful, thank you. Thank you, Mansoor. Any questions?
I have a question for you, Mansoor.
Sure.
Great presentation, by the way. So it's regards to your reward function. Were you able to identify which of those terms was more important in terms of getting a stable results and reaching convergence? Like, could you leave out 1 or 2 of those terms and just work with one, or are all 4 of them contributing equally towards your solution?
So you are asking which components are important. Did we verify that? So
yeah.
So we first started out with price and carbon rewards. For individual case, it was definitely important. And we experimented a little bit with different weights assigned to them, and equal weight was working quite well. And then ramping and load factor rewards together, they definitely helped. And separately, they also helped, but less. So I think we verified that both rewards help a little bit, and together they help a lot. And these rewards in particular improve the grid cost, and they also improve, as a result, they improve the overall cost a little bit too. And the final reward weights, we didn't experiment too much, but after some little experimentation, we found that these weights are pretty good.
Okay, thank you.
Thanks.
Thank you. Any other question? Yeah, Julian?
Yeah, yeah, very interesting. Do you know what's the difference between just using the rule base and using the rule base with the deep reinforcement learning? Was there much of a difference between like simply using this rule base and
yes, according to validation scores, there was big difference. Like I don't remember the numbers, but it was big enough that we were very confident that using both is better than using just rule-based or just deep parallel agent.
Okay, cool. Thank you.
Thanks.
Thank you. Any other questions? Mansoor, I had one quick, you mentioned a few times that you're using the past 16 days average. Is there a reason you picked 16 and not 15 or 18, or how did you come to that number?
So I did lots of cross-validation experiments on training buildings, and the R2 score we were obtaining was better for 16 days than for other days. And even if I included several windows like 16 and 14 and 4, keeping just 16 was the best choice, at least in our experiments.
I mean, 16, I'm asking because 16 seems that it's biasing the data a little bit to the, like it gives a little bit more to like the hour before your current time step, right? If you look at it like, or I mean the days before you like, so I don't know. I mean, that was trying to think about if that made sense or not. But anyway, it like it's kind of like right before the same day, like comes more often, right? So if you're a Sunday, then Saturday would show up more often than a Monday in your data set, right? If you average in the past 16 days. I think that's what I was thinking if you hadn't thought, but if it's optimized on feature, then it might be just numerical. Cool. Well, there's something in the chat. Oh, okay. Yeah, Danielle just puts it data-driven decision. So that's good. Sometimes it's the only explanation. Thank you. Oh, wonderful. Thank you, Mansoor. Next up is Team Greener. And I believe that's Sean. Is that correct?
Yes. So can you hear me?
Right. Yes, we can.
Okay. So hi everyone. This is Shen Zheng from Microsoft Research Asia, and I'm very glad to share with you our solution for the CityLearn challenge. And so first I will recap the background, and our intention is to demonstrate the potential of AI for the building's energy management, and we leverage the CityLearn environment, which couples the real-world data with simulated batteries to demonstrate this potential. And so the objective we want to optimize can be divided into 3 types of costs. The first is we want to minimize the overall electricity price costs, and we want to minimize the specific carbon intensity emission cost for each building. And we also want to do some load shipping, and the load shipping costs have been divided into 2 parts. One part is to penalize the differences between 2 consecutive steps, and another part is to penalize the gap between the monthly mean and the monthly maximum. And so for this overall objective, we can issue the action for each building at each time step, and the action can turn into the energy consumption of the battery, and then it turns into the building's energy consumption, and then we can compute the overall objective. And our decision can be made by leveraging all the observations, include data information, weather, energy, and so on. And based on our understanding, the most challenging point of this problem is that we have a huge parameter space. That is, we can the action for each building and each time step, the range is from -1 to 1, and we have an exponential growing space of these actions to search. So this huge parameter space is the biggest challenge of this problem. And another problem is that even we have the data, we have some historic data, we have some for some known buildings, and we need the model of agent to generate to some unseen scenarios that include the different number of buildings, include the different workloads, and even the building's number can change, the workloads can change, and also the price variations and the carbon intensity, they may also change. Although in our case, the price and the carbon emission, these 2 series may not change. And for the more challenging scenarios, this will also change too. And so for these 2 challenges, 2 key challenges, our solution can be summarized into 3 parts. The first part is that we want to solve this problem in polynomial time. That is, we want to tackle this exponentially growing the parameter space. So the first step of our approach is to minimize a surrogate objective, which is similar to what the other teams have shared before. the insight here is to find an upper bound of the original objective and then solve it in polynomial time via dynamic programming. So for this part, I will introduce later in more details. And after we obtain some dynamic programming produced solutions, we can leverage a learning approach using multi-agent imitation learning to learn those expert demonstrations. And we wish that a well-trained policy network can help to generalize from the thin workloads to unthin workloads. And if we use maybe more different expert demonstrations, so this agent can learn diverse behaviors, and then they can contribute to the more robust generalization. So for the robust generalization part, we have tried the two critical techniques. The first one is the policy ensemble. That is, we have seen that if we ensemble diverse policies, so we can clearly see the performance improvements in the during the CityLearn evaluation. And another one we have tried is to build more simulated environment. The insight is to augment the environment data so that we have a new environment and we can test the transferability of the trained agent, and we can also use that environment to train new agents. And so let's see the first part. The first part is to minimize orthogonal objective. The core insight here is that we find an upper bound for each type of cost. And here the key technique is to change the order of the summation and the max, or the summation of the absolute operator. And here for the price cost, for the emission cost, and the ramping cost, we can easily do this. But for the penalization for the the gap between the monthly mean and the monthly maximum, it is difficult to use this technique to do this. So we omit that step at this stage, and we focus on the optimization of the first three cost sub-objectives. And then after we find the upper bound of the original objective, we can use the dynamic programming to efficiently optimize those objectives. And then we can obtain the actions. Maybe we can treat them as the expert demonstrations that produced by the dynamic programming. And here we the hyperparameters that we have tried is that we explore different configurations here, such as we can tune the action limits ranging from the -1 to 1 into the -0.1, 0.5 to the 0.5. And we have seen a clear benefits by reducing the action limits, because it helps the neural network to limit the output range of the neural network, so that the neural network can better generalize. And we also try the different assignments of the non-shiftable loads and solar generations to different buildings batteries, so that we can enable cooperation or the load sharing when we do the optimization, when we do the dynamic programming based optimization for the upper bound objective. And also try different weighted combinations of this upper bounded sub-objectives. And then we use all these different configurations to obtain the actions that produced by the dynamic programming algorithm. And we trace all these actions as expert demonstrations demonstrated by different experts. And after we obtain the actions produced by the dynamic programming, we use the multi-agent imitation learning to train a network that can imitate those actions. Here we use one shared parameter network for all the buildings. That is, for all the buildings, we only have one set of parameters, that is pi theta here. and the pi theta takes the observation as a step t and emits the action. Action here, we use the a hat to denote that, and the imitation loss is the square error between the difference of the imitated action and the action produced by the dynamic programming. Here, the most important part of the multi-agent imitation learning is that when what we fit into the environment, CityLearn environment, here we have seen that if we should fit the model predict actions into the state transition, and then in the next step, we still predict the act demonstrations. In this way, we can enable a stable training and a stable generalization. And after introduce the first two steps, that is find an expert demonstration and build a network to imitate those DP actions. We have tried two critical steps to obtain a robust generalization. The first is the policy ensemble, that is build the expert demonstrations with different dynamic programming solutions, and then take an average ensemble approach, that is build an ensemble agent that average all the well-trained imitation agents output. And we also do the environment augmentations, and these two lines are independent. We can create new buildings with similar workloads by the mix-up idea, which is to take a weighted combination of all the existing buildings and create a new building. For example, for the non-shiftable load, we can use the alpha coefficients to do the weighted combination. Here, for the solar generation, we can use the beta coefficients to do the weighted combination. And these coefficients can be sampled from a Dirichlet distribution with certain priors. If we want a new building to be more like an average of all the buildings, we can make the prior larger. And if we want it to be similar to some specific buildings, we can reduce these coefficients. And we have tried different configurations, and we find that if we fix the training environment and we generate another environment with different buildings workloads, and the performance can drop significantly. So we have tried to build different types of augmented environments and test the transferability of these agents. And we also use this augmented environments to train the agents, and use that agents to as our submissions to the phase 3. And our results, finally our results on the phase 3 leaderboard, public leaderboard, is about 76%. And here we have seen that since we do not optimize the load factor cost specifically, so here we have seen that in the maybe the September, the month is ranked in the 9th month. We have our cost is even larger than the original one. So we think for this cost we did not perform well, but for all the other, such as all the other costs, such as the price cost, emission cost, and the ramping cost, and the orange lines indicates the results produced by our agents, we have clearly seen the cost reduction. And we also track some cases, and we can see some collaborative behavior, and we can see that a shared policy network can handle different workloads. And here, based on the maybe 2 or 3 months study of this problem, we find that although our results make sense, to some extent make sense, but we need to pursue more exploration on the collaborative mechanism, because our current method do not have talents on this part. And our future work is to integrate the current approach with the global Q-learning, so that we can start from a good imitation, and then we can learn from trial and error, and until the convergence. So here is this is what we want to do next. And also based on this problem, we think that for the other same type of optimization in the energy market, we may formalize a general framework that is do the sequential decision for multiple agents and to fulfill a joint objective across spatial and temporal dimensions. And that's all of the talk. Thanks for the listening.
Thank you, Sean. Any questions from the audience, comments? Very nice presentation. Thank you. Julian?
Yeah. Hi. Yeah, thank you for the presentation. I was curious, can you go back 2 slides?
Which page?
Yeah, one more with the results and the. I know the one just after that, where you can see the with battery and no battery.
In this page.
The next one.
The next one.
Next one.
Yes.
Okay.
Yeah. So the bottom one, it's super smooth. Is it like with perfect forecast this, or does it learn to be this smooth, like the with battery plot? Because like for us, we had basically an error on the next forecasting step, and it was super difficult to get it very smooth.
Maybe this is not the forecasting based solution, because our solution is the imitation learning based, and the imitation agent use the actions derived from a dynamic programming. While the dynamic programming is a global optimization stage, they can see not only the past information, but also the future information, so that he can, this method can make the this consumption series much more smooth. And then if the agent can leverage the historical information to learn that, so that if it imitated enough good, so it can also produce the similar behaviors.
Okay. No, it's impressive. How smooth it is. Nice. Thanks.
Yeah, if you can create a constant net profile to the grid at a substation level, everybody will be very happy. Any other comments, questions? Okay, well then thank you again for this nice talk, and we'll come to the final presentation, I believe. That's Team Together.
Yes.
Jane.
Can you hear me, Zoltan?
Yes, we can. Mm-hmm.
Okay, so I'm trying to share my screen.
We can see your screen.
Great.
The floor is yours.
Thank you. So hi everyone, this is Wei from Alibaba Demo Academy. Today I'm on behalf of Team Together to present our method in CityLearn challenge. Basically, we propose an ensemble approach for forecasting optimization and the reinforcement learning. In this challenge, we have data from a community with multiple buildings, including the electricity demand and solar generation of a full year. So we aim to provide the decision support of energy storage devices. In this challenge, we observe 2 key issues. The first one is the uncertainty for the solar generation and load, as the solar generation can be influenced by the weather condition, and the load is fluctuated with respect to the hour of day. In addition, each building has its own load characteristics. And the second key issue is the multi-objective, since we aim to optimize the economy, low carbon, and grid stability at the same time. So to tackle these challenges, we propose a solution of two-stage dispatch. That is to say, we firstly forecast the future load and solar generation, then perform the battery dispatch based on the predicted values. So firstly, we focus on the stage 1 of forecasting. We train a tree model or sequential neural network using the trained data set. Important features can include the historical time series, including load and solar generation, and also weather forecast values. And after we obtain the trained model, we apply them to infer the next days or next hours load value and solar generation. So you can see in this plot, the black curve represent the real value and the red curve represent our predictions. Then we apply this, after we obtain this predicted value, we aim to provide the battery dispatch. We follow 2 branches of methodology according to the literature, including a reinforcement learning one and a stochastic optimization in parallel. So the first method is reinforcement learning. We'll train the agents to interact with environment to take the actions according to the observation. Here in the plot, we provide the basic model architecture. To look into details, our environment is the same as the CityLearn simulator, and we introduce essential features including weather, solar generation, and load and other informations, including the forecasting values, to enhance the observations. In terms of pre-processing, the observations are filtered and normalized, and in the procedural post-processing, we mask the action space according to the battery constraints and the SOC of the buildings. Last but most importantly, we train the multi-agent reinforcement algorithm to achieve the building coordination. As defined in the objective of price cost and grid cost. And here it is the MAPO algorithm. So in the MAPO algorithm, we consider the number of agents is different across the 3 phases. So we use the learning framework of centralized training and decentralized execution. Detailing speaking, in the training process, we train the joint policy of team with global information to maximize them, and we maximize expected discounted accumulated team reward, as you can see in the formula. And next, in the execution step, each agent makes its own decisions based on the local information. In addition, in MAP algorithm, we do the parameter sharing, since we consider to incorporate the homogeneity of the agent structure, and thus it can also improve the generalization ability. So in addition, in this problem, the team rewards for each time step can be decomposed as this formula. And what is important issue is that this ramping or this load factor term is relevant to the maximum value of each 713 time steps. So it's very hard to sampling from get trajectory from this reward at the beginning. So we first sample this trajectory at the beginning with an incomplete reward, and then replace this reward by the real one and we use a modified trajectory for the update. And now we switch to another branch of methodology for battery dispatch. Here we mainly based on the model predict control and stochastic optimization. We first extract the learning objective, optimization objective, and the battery constraint from the CityLearn environment. That is the average of price cost, emission cost, ramping, and the load factor, but in a mathematical form. And also here we have the constraint of the state of charge. To facilitate the optimization solving process, we linearize the model by adding and replacing the variables and constraints, including, so here we include the net consumption, state of charge, volatility, and also the monthly statistics. So finally, we have a linear problem. To solve this linear problem is very quick. But here is a problem about this LP problem, because we don't have the future information of load and solar generation in the current state. So therefore, to tackle the uncertainty of forecasting, we propose to using the stochastic optimization for the daily dispatch. To look in detail, we add the Gaussian noise on the predicted value, and we propose to generate a multi-scenario optimization problem, which we can solve them coordinately. In addition, several techniques of predictive model control have been involved in our model. For example, the rolling horizon control, as we can see in this plot. At each time step t, we predict and optimize for the next 24 hours. And then after several hours, for example, this big T hours, we take the new measurements and correct the previous predictions and actions. So the whole procedure is repeated for the full year. Besides the rolling horizon control, we also apply the self-adaptive prediction adjustment, because we consider the data drift issue. So at each time step, we adjust the predictions by comparing the historical value and the predicted value. And we can define the adjustment parameters in this formula. Okay, that is our main methodology. And now we provide a brief summary of our empirical results. So the best submission in online public leaderboard is the two-stage methods of forecasting, followed by the stochastic optimization with an average score of 0.728. And we empirically show that these methods outperform the equal certainty deterministic optimization methods, and also the reinforcement learning methods. And in the offline part, we have also tested the ensemble of reinforcement learning and optimization-based methods. In the training data, we ensemble according to the time periods, and we observe that we can gain additional improvement given the complete information. And besides, we know that the offline testing data set is made based on the combination and average of the training data. And we also perform hyperparameter tuning according to the performance offline. And also, we also consider the 30 minutes online time limit. And finally, let me show you our modeling and programming tool, which we use for data analysis and solving optimization problems in this challenge. So with our MindOpt solver, we can optimize conflict system for reducing cost and increasing efficiency. And with MindOpt Studio, we can easily access the real-world decision-making issues and their solutions in this online platform. So for more information, please don't hesitate to contact us. We are Decision Intelligence Lab from Alibaba Demo Academy. So thank you very much for listening.
Very cool. Thank you for the nice presentation. Any questions or comments?
Yeah, maybe one question for the final results. I think the previous slide.
Yeah.
The ensemble worked better on the phase 1 data, right? Or
in fact, we only tested the ensemble in the phase 1 because that was the last day, so we don't have much time to put it online. So we tested it offline, and we just ensemble according to the time period. And surprisingly, we find that it have a bit improvement compared with the single model.
okay, and so the what you submitted and obtained the best score in submission was the MPC, the stochastic optimization part, right?
Yes, just the same as the other teams, we also to judge if the data from the training or the testing. So in fact, this one, stochastic optimization, is for the unseen data set. And for the trained data set, since we already know all the information, so we can conduct this optimization and reinforcement learning given all the complete information offline. And we just, this is our best result for the training data.
I have a, yeah, Evgeny here also joined. I have a question about the stochastic optimization part. You mentioned you used the Gaussian noise to simulate multiple scenarios. What's your method for estimating the parameters of the Gaussian distribution?
Okay, thank you. So for this Gaussian noise, we just have to decide two parameters. One is the mean value, and the other one is the standard deviation. And for the mean value, we just take the results of the load and solar prediction as mean. And for the standard deviation, we just compare, we just obtain the from in the offline part, we can estimate such a standard error of our prediction model. So we use this error as our standard deviation.
Is it same in every hour and every time step, the variance?
In fact, because we estimate our prediction model is for the next 24 hours, and we can observe that the prediction error is much less if you for 1 hour, and for the 24 hour, the error is much larger. So in fact, the standard deviation is different.
Yeah, thank you.
Yeah, thank you very much. That's very nice.
Other questions, comments?
Hello. I have a question. That is, can you explain the insights between the performance gap of different methods on the online evaluation and the offline evaluation?
Oh, the gap. Okay.
Yeah.
So first,
we can see that for the offline evaluation, the reinforcement learning and the optimization do not have a significant gap, but for the online submission, here is a significant improvement by leveraging stochastic optimization. So hello.
Oh, we can't hear you. Yeah.
Yeah, we cannot hear you.
Sorry, can you hear me now?
Yeah, now it's working
Yes.
again.
Yes.
Perfect. Something wrong with my earphone. Okay, so the difference is that in online, we have to do the prediction for the load and solar. And in this stochastic optimization, we have done a lot of rolling horizon control and also the self-adaptive prediction adjustment for these methods. And somehow we because there are data drift issue, the distribution of load and solar are different across different building, because we have done this this trick for the method of optimization. Somehow we can correct these biases, but for reinforcement learning, we didn't perform such tricks. I think that is the gap online.
Okay, so for the offline data, when you use the reinforcement learning, do you still encounter this context drift problem?
You mean in this algorithm, because we already know the future information, so we just put the future information in the reinforcement learning?
You mean this part you leverage the future information, so not just the observations before the current time step?
Okay, yes. Let me clarify this point, because in our reinforcement learning algorithm, we take the prediction value as part of our observations, part of the states.
Okay.
And
so for the
offline
data. Okay, you see.
Yeah, in the offline, we just take the real value. So that is different.
Okay, got it. So if in the offline data, you also use the predicted value, the reinforcement learning model will perform maybe worse?
Yes, you're correct. Yes, exactly.
Okay, got it. Thanks.
Thank you.
Very good. Any other comments or questions? Awesome. Voila, thank you. Thank you for this presentation. Thank you all for the presenters. I learned a lot. I'm excited to see so many different types of solutions. And with that, we'll move to the final part, or this almost final part of this workshop, which is the results. And you know, we had to make a selection. I mean, you made a selection by submitting the algorithm, so it was data driven, so to speak. So I wish I would give everybody all the prize we have, but NCVA also didn't give us so much money, so we had to what we have. We had to work with that. So with that, let me just recap what Siva said in the beginning. So we're quite excited how many people collaborated, how many people submitted solutions for various reasons. One, I think again to recap what Siva said in the beginning, this is a very, very interdisciplinary field. The problem comes, from power systems, from energy, from buildings, but then the solutions came from, CS, AI. And so there needs to be sort of like a meeting space where we can explore solutions in a realistic way. I have attended a lot of CS presentations and conferences where I was like, yeah, this is a great solution, but there's no way, anything of this would happen. And likewise, I've been in building places where the approaches that could be done are so, simple that there's a lot of potential missed. So what we're hoping a little bit here is to create a forum with CityLearn, but also as a community to work together and learn from each other a little bit. So you see here the numbers. I mean, 600 participants, 100 teams. I think in the last phase 3, still we had about 35 or 40 teams that submitted to the final leaderboard. So it's amazing. So thank you all really for that. I wish we would have 20 presentations, but also I don't want to sit through a full day and be mindful of all of your times. But again, very, very thank you. You see the breadth of where the solutions came from just by this top 5. We had Asia, we had Africa, we had US. And I think if we had expanded to top 10, we would have also gotten Europe and South America. So it was really, really international and interdisciplinary also from where the folks came. So very, very cool and exciting. And so it gives me also a lot of energy and motivation to do another challenge next year with a different topic, but in a similar spirit. So we're working on that already. So just to keep your eyes open that this is continuing and it's not the end, but more like the beginning. So that's very exciting. The other thing, and again, the community platform that AI Crowd provided was really cool. You could see people working together. We had folks discovering bugs throughout the process, especially in the early stages. Submitting pull requests to improve some parts of our code, which was also very exciting and also useful. People provided notebooks to get started. So some of that is, I'm forwarding it to other people now who ask me how they can get started. So it's really, really cool crowdsourced, endeavor. And this is also why, we decided to give out awards for community support. So these are folks who, fix bugs, provided pull requests. Somebody, said, oh, we fixed some of your routines and it's like 10 times faster now. Others, provided codes. And just generally good discussions and being good community members. And I think that's more important. While this is a challenge, it's intentionally NeurIPS calls it a competition track. I don't like the term because we try to provide solutions for global warming and climate change. So competition is maybe not the right term, but a challenge as a community is a lot better. And so this is also why I like the fact that we do have community awards. And these are sponsored by SIG Energy, as I said in the beginning. And so without further ado, here are the 3 that we were able to identify. Ludwig from University of Tübingen in Germany, Qi from Shenzhen University in China, and Julian from Brussels, Freie University of Brussels. So congratulations. You deserved it a lot. Like I said, I don't know what any of you did individually, but all of you together, I believe, sharing a lot of code, providing a lot of discussions, and improving the code base. So thank you for that very, very much. You will get, I'll get in touch with you separately. You can pick your favorite conference, BuildSys or eEnergy, which are the ones sponsored through SIG Energy. I don't know where BuildSys will be next year, but I know that eEnergy will be in Florida sometime in the summer. So hurricane or nice weather, you can pick, I don't know, something will happen. No, it'll be nice. And eEnergy is happening with FCRC, so it's like a big, like 7 conferences at the same time from this computing community. So that will be probably very nice. Okay.
Hey, Zoltan.
So, yeah.
Your screen isn't sharing. I don't know.
My screen is not sharing. Oh my God.
Yeah.
Oh, really? It shows broadcasting. All right, let me try it again. Oh, sorry. So you missed a big part, people. Sorry. The most important part. Let me try it again. Here we go. Okay. Can you see this?
So what it shows is screen broadcasts, kind of like.
Really?
Yeah, it's not showing the actual slides.
Okay.
I don't know if it's just my end.
Let me try again, and if it doesn't work, then we'll go through your slides.
Yeah, it looks like it's a different monitor or something.
Okay. Yeah. Well, maybe Musk needs to buy Apple and fix the pads. We'll see. Let's see. Okay, I'll give it one more try. Does it come now?
It says double click to enter full screen mode. So
yeah. Okay. All right. Let's move to you, Kingsley. I'm sorry.
Okay.
Then in this case, I have to capitulate. Wow, that's embarrassing. All right. In the big moment. Oh crap. All right, you share your screen and then and then I will just say next slide, please. Oh, it's way to build tension, right? Like it's right now, like, oh my God. Anyway, I did say the names, Ludwig and Julian and Kia, did I pronounce your name? So congratulations, thank you a lot. I think very helpful and for the community as a whole, because I think it improved all of our solutions at this point, especially finding bugs. It was very, very humbling to create some code and put it out there to people to check and complain about it. And so that's, I think that I learned a lot from that experience, and it humbles you a lot to make code that works for others. Okay, so here it is. This is a slide, where I was on. So the again, BuildSys, I don't know where it is. I will be actually chairing BuildSys, so but I still don't know where it's happening. And then eEnergy is happening in Florida, so we can in sometime in June or July, I believe. So hopefully that. And so I'll be in touch with you, and then you can pick. All right, thank you. So the next slide, please. Now we move to the competition winners or the challenge winners. Next slide. Third one is team or I believe you're alone. Team CUFE from Egypt. So Michael Ibrahim, congratulations. Well done, Cairo University. Well deserved. Then number 2, next slide. Next slide is Team Ambitious Engineers, Matthew and Sropong. from Washington University, University of Washington, University of Hawaii. Second place, congratulations, well done. And now drum roll. And the winners are Team Together, the Alibaba Group. The last presentation we saw, congratulations, well done. And thank you for participating, really. I think all of you and also Div Model and Team Greener, who we had to bypass, or I mean, who didn't make it in the top 3, but obviously everybody is a winner, and especially science, I believe, and engineering in this case. So hopefully this helps everyone. Shiva, do you want to say something, or anybody else at this point?
No, I'm thrilled to see that we have such an amazing competition, such an amazing participation, and congratulations to all the teams, and especially to the top 3 winners. This is absolutely phenomenal. Your solutions are moving the needle, and in the right direction. I'm just thrilled. Thank you. Appreciate it.
Thank you. And so what will happen in addition to these, we'll write the paper, and we'll invite all of you, the top 5 teams, to contribute your solutions. And also the code bases are released publicly, so people can profit from that. And I will be in touch with that separately. So thank you very much. So what we'll do now is to try to hang out a little bit. So go to the next slide, please, Kingsley. I think that's the one. Yeah, the next one. And so we'll mimic a little bit of hanging out while dropping you into some of these rooms. I think Kingsley already prepared it. We'll just randomly